We are Team Pegasus from the University of Southampton, and this is our Mars rover. In this Systems Acceptance Review video for the University Rover Challenge, we will outline how we hope to be the UK's first successful entrant to the URC in Utah this summer.
Our chassis is built around aluminium X-bars that offer a sturdy frame, the adaptability needed to alter our rover between competition tasks. Our suspension system is based around the rocker bogie design and is built from curved stainless steel plates and aluminium bracing, making it a strong and lightweight design with enough clearance to tackle the obstacles that we found at Utah. The rocker bogie design relies on a differential formed of 4 bevel gears. This allows the rover to keep all 6 wheels on the ground while tackling obstacles on the extreme retrieval task, while maintaining a level chassis. Our wheel design, which is currently being manufactured with the help of Protocase, consists of an aluminium spiral spoken rim with rubber grouses. Our industrial partners, Airbus Defence and Space, have helped us optimise the design of the grouses that will give our rover increased traction on the sand and loose soil we will need to traverse in Utah. For testing on hard surfaces, and while the new wheels are being manufactured, the rover is equipped with modified go-kart wheels with specially designed 3D printed wheel hubs that offer a modular design that will allow us to easily swap between the 2 sets of wheels. We have designed a 5 degree of freedom arm and wrist assembly that will give us the strength and dexterity needed for the extreme retrieval and equipment servicing tasks. 3 linear actuators control the angle of the linkages, while the rotating base allows the whole arm to turn through 360 degrees. Our wrist design allows us to control the orientation of the gripper to precisely manipulate objects, and our 3D printed gripper is a multi-purpose 4-bar linkage design that will allow us to pick up and move objects in extreme retrieval and equipment servicing tasks. We have tested our gripper on a 3 degree of freedom prototype arm, which allowed us to test our control software and range of motion. Our new arm has significant weight savings with improved range of motion and increased dexterity.
For communications, we have installed a long-distance Wi-Fi antenna on both the rover and the base station. We have calculated our communication systems will provide us around 40 megabits per second of data transfer, more than sufficient for video streaming across all tasks. Safety is a critical part of the electronic systems, which includes overcurrent protection and a LiPo battery alarm. This will warn us against potential battery malfunction and over-discharge to ensure the electronics remain safe at all times. We are using a modular electronic system to enable parts to be tested separately. This will accelerate the design process and allow us to quickly change focus between tasks.
We are using the ROS framework as it offers many pre-built packages and greatly simplifies data transfer between the rover and the base station. For the autonomous traversal task, our rover will use an extended Kalman filter fusing sensor data from the onboard accelerometer, GPS unit and wheel encoders, along with visual odometry from the cameras. We will use this and depth sensing from our front-mounted Connect camera for simultaneous localization and mapping using a pre-built ROS package. Once we near our goal, we use OpenCV to identify the tennis ball marker at the end position and determine its distance from our rover. To test our sensor fusion techniques and autonomous navigation in a safe environment, we have developed a simulation of our rover in Gazebo. This simulation has been verified with physical testing traversing difficult terrain.
When looking for signs of life in the science task, it's practical to look for optimal conditions. This means looking for evidence of liquid water, such as channels and valleys. Once a promising site has been selected, context and a stratigraphic profile will be captured using onboard cameras. An earth auger will be used to collect the sample from below the surface. This will be stored in a sterile, sealed plastic container for transport to the base station. Onboard testing consists of a soil probe with sensors for temperature, moisture and pH. At the base station, the sample will be tested for biomarker macromolecules such as proteins and lipids using staining and fluorescence microscopy. Lipids are more resistant to degradation than nucleic acids and proteins, so are more likely to be preserved. Commercial test kits will be used to identify nitrates, phosphates and potassium in the sample, and hydrochloric acid will be used to test for carbonates, which can be signs of historic liquid water.
We have been extensively testing our rover and its components over the last year. We have built rigs to destructively test a prototype differential and wheel hub. This will ensure these crucial components can withstand the forces required to compete in the URC. Our testing plan culminates in taking our rover to Airbus's Mars Yard, the testing facility of the ExoMars rover developed by the European Space Agency. This is a great opportunity to fully showcase our rover's capabilities in a state-of-the-art facility. Thank you for watching. We are Team Pegasus.